Hello everyone and welcome back. In this video I will show you how to use IDA Pro as a disassembler and a debugger. So in the previous video I showed you how to take this simple code, and by using this release mode we compiled a x86 or 32-bit version of the P executable. After we did this, we loaded the P file into IDA Pro. So what we can see here is basically the disassembled code, which is basically represented as a machine code or as an hexadecimal representation. IDA takes all of this hexadecimal code and disassembles it to a more human readable form. In the left pane here, we can see the subroutines which are defined or recognized by IDA. So for example, a function that is defined by the developer, like this print sum function, IDA cannot really know the original function name the developer gave. It really depends if you have the PDB file or the debugging symbols, so IDA can recognize the original name, but without the PDB, it cannot really do it. So it will recognize it as a function and will put it context as a subroutine. So this sub is subroutine, which is another name for a function, and then it will put underscore and the starting address of the function. So if we do double click on it, we can see we do space that we have the sub and 401000, which is the starting address of the function itself, which we can also see that it's under the text section. If you remember from the previous videos, I explained shortly that the text section, the default name for the section where all of the machine code, where the actual code is executed by the thread that executing the code inside a process. So if we want to go back, we do escape and do space. So we can recognize that we are in the main function, and we have some assembly instruction and call to functions. Now, in order to understand what is the context of this function and to make our life easier, we can double click on this subroutine and see the inside of the code. If we want to go back, we can do again escape, or again, we can just double click and get into it. So from what we can see here, the printf is basically used here. Now it can be very strange sometimes because in the code we see printf, but in the disassembled code we see a little bit different stuff like this vf printf something. So as a reverser, you don't always need to concern yourself of why things are like this or like that, and just understand and recognize the context. You understand if you execute this function while debugging, you see that it will actually go and print whatever it needs to print. So if you want to rename this, we can do right click rename, or basically use the N key in our keyboard. Let's rename it to printf. And now we can basically see that the function or the subroutine is changed also in the function name window, and we see printf. So now if we do escape, now we see a different context. Now we can understand that we actually use printf here to print, for example, the string of while loop is printed by printf. So now let's try to understand the code here. So the first thing that you will notice in each function, whether it's the main function or any other type of function, that it will start with some, maybe for some of you that will not recognize it or not necessarily know assembly, can be maybe strange, but the first instruction that you mostly or likely to see is push EBP, move EBP SP, which is basically the stack initializer. It's what initializes your stack memory to be used by the function. So basically each function is initialized with these two instructions in order to initialize the stack for the operation of the rest of the function. So this is called the prologue. The prologue is the starting of a function. And the end of the function, it's called the epilogue. The epilogue, you will mostly see something like with pop and return. Okay. After this, mostly we'll see some cleanups of the stack. Whenever you want to clean up a stack, you use the add. I know it can be counterintuitive, but the stack actually grows downwards. So whenever you use add, it cleans up the stack. Whenever you do sub, it adds or basically uh, um, fills it with more data. So add basically cleans up the stack or removes stuff from the stack. So while the ESP is pointing to the top of the stack, the EBP is pointing to the base of the stack. Of course, if you want to more understand about, you can research it. But as again, in this course, I will give you only the basics and the most important stuff for us to understand the basics of the reversing journey or the malware analysis that we do in this course. So if we go to the source code, we see that printf takes a parameter. So each function needs to have a parameter. Not all of the function need to have a parameter, but for example, we can see the main function doesn't have any parameters in it, and that it takes, but the printf takes one parameter to be printed, and potentially can take more parameters. Or the print sum, which is a function that defined by the developer, gives or provides two parameters, as you can see here, defined by this void print sum. So if we go back to IDA, we'll see a little bit different styles. So before we see the call printf, those parameters need to be pushed to the stack, so the call to the function can be used. So if I want to, for example, print the while loop string, I push the value to the stack and then I call printf. So think of the stack like the ammo or ammunition or the function of printf to be used while the function is actually in operation. So before you have a call to a function, you have push. Now it really depends. Whenever you use x86 code, you'll see pushes and call. x64, it really depends, but most of the time the first 4 parameters will be moved to 4 registers, which we will see in our next example for the next video. And then it basically from the fifth parameter and so it will take the parameters of the function, basically push it to the stack. So it really depends on the architecture or the binary, if it's compiled in x86, x64, and other stuff. But the most important thing for you to understand is the ability to recognize patterns. And by recognizing patterns and functions, you can get better understanding of the code. So we can see here push ESI, EDI, some registers. Again, there's a push to for loop, and then another move for 3 for ESI for some reason, then call printf and cleanup of the stack, and then XOR EDI, which will give us 0. Then we have a nope, which is no operation. Why the compiler decided to put this nope, I don't really know. If you want to go deeper in why compilers want to do this thing or that thing, you can research it. I can give you a lot of reasons, but not all of them will be correct. It really depends. Okay, so then again you have push EDI, this offset, printf, and again you have some loop here, and you see this comparison of if 5 compares to the value in EDI, and it jumps lower. So if the value in EDI is lower than 5, it will get a jump and do the loop. So it basically, this is the for loop that we see here. If it's lower than 5, we'll jump the loop. Now, in the previous video, I basically said that I will also show you the pseudo decompilation window. So if I do F5, I'll just put the window like this and synchronize IDA view. I will see the real power of using both of those windows. We can recognize this for loop basically. So if you highlight the for loop, you can see, okay, so we have here this code, which is part of the loop or whatever, or To be more specific, you see this increment, add, compare, jump loop, or jump lower. So this is basically the implementation. So in C, it looks like this, and in assembly, it looks like that. If you go and highlight the printf here, for example, it will literally highlight the code. So it's not literally the source code, but it's kind of close to the source code. So this is why it's called pseudocode. So you can learn a lot from it and can help you in your journey of reversing. And of course, if you want to debug the program, you can do it. Now I'll show you in a couple of seconds. Before this, we have other windows like the hex view we saw earlier, with the structures. Those are basically to define the structures of functions, Windows API functions, stuff that are corresponding to stuff of the operating system itself, and really depends on your reversing journey. Especially, we'll use it on advanced reverse engineering whenever we need to define structures for our own or structures that are not known to IDA to aid in our reverse engineering. We have imports. Imports is basically the functions that are imported from outside of the code. So those are the functions that are imported by the linker of the operating system. We have the function that is important. For example, we have the exit function, which is imported from this DLL API, MSWin, whatever. We have the, let's see if we have the printf here, for example. We have the printf. So Visual Studio or the compiler of Visual Studio decide to import this stdio common vfprintf. Maybe it's for optimization purposes and stuff like this from this DLL. Okay, or it decide to add this get current process from the kernel32.dll library. So we see here the function name and the library that is imported from this library, basically. Okay, you have exports. Exports are basically, you will see, so if imports are the functions that are imported by process or by P executables from DLL files, the opposite is true for exports. Exports where DLL files export for other P files. So if we load into IDA, for example, or into X32DBG or any other type of disassembler or debugger or a P view program, and we load the DLL, the exported functions. Okay, this is the reason of DLL files to export functions for other exes or exe files. But of course, because they're the same format, an exe file can also import and export, vice versa for DLLs. So in order to do in order to start the debugging, we need to put somewhere a breakpoint. We can put in the start of the program, we can put in other places. Take into account that if you put a breakpoint here, for example, it will execute all of the code till this point. So take it into account. So if you have something to like anti-debugging technique or something that you need to bypass, you need to take it into account and to tackle it before you get to this point. So if we put a breakpoint using the F2 in the keyboard, or just do right click and add the breakpoint, we can start our debugging. So let's do here local Windows debugger and start. We can close some windows here. Like we have the threads that are running, or the modules that are important from DLLs, or the DLL files itself, or from where the actual module or Windows API functions imported. So now we see here the IDA window. We can see here the stack, the hex view here in the left, and the registers here in the right pane, and the CPU flags. So the register we have EAX, EBX, ECX, EDX, ESI, EDI. ESI and EDI are used for source index and destination index, mostly for moving something from a source memory to a destination memory. For example, if you use the function of memcopy, Mostly it will use the ESI as the source address and ED as the destination address. This is the way of how things work. EBP-SP, as I explained before, is the stack, is what basically defines the stack frame. EBP is for the base pointer, ESP is for the top of the stack. EAX through EDX are basically, each one of them has their own definition, but they used as general purpose registers. And in EAX, you will have the return value of a running function. So for example, if we run the printf function, we'll have a return value from the function. So just as a short explanation about return values, each function we can define whether it has a return value or not. The return value will give a status, whether the function is succeeded or failed or something else. So it really depends on the definition of the function. If we use void and then the function void, you will not expect from a void to have a return value, because void is without a type. It's not an integer or char or other type. Because the main function has the type of int, you expect to give some type of return value. Maybe either 0 or -1. And it really depends on the definition of the developer. One developer can define that 0 is a success and -1 is failed, and the other developer can do it otherwise. Throughout our course, we'll see different type of Windows API functions, and you'll see different cases. It can be sometimes very good, sometimes very annoying. But for this, we have the documentation of the MSDN, Microsoft documentation for functions. And we'll see by going in this course. So we have a return value of 0. So if this function of main will succeed, we have the return 0. If not, we'll maybe have some other return value. So this is what basically the return value will be stored after the function will be executed, will be stored in the EAX register. Now take into account, the register originally is AX code. AX is 16 bits. It has a lower address, which is called AL or accumulator lower, and AH, which is accumulator high. It has a low and high. Then you have the EAX or E, which is for extended 32-bit. Then you have the RAX, which is 64-bit. If you compile a P executable in 64-bit, Visual Studio, for example, the RAX, RBX, RCX. Okay, so let's do our debugging. So we have F8 to step over and F7 to step into. Now let me explain it. So now if we do F8, this push ESI instruction is executed, and this value in the ESI, we can see that this is the value, debug whatever something. We can click here and see what it is. We can try to do here DDD for definition. It will change it from, for example, if we do Control Z, from before it was DB for byte, define byte, then it go for define word, which is 16-bit, and then define D word, which is double word, so 32-bit. Then you can see basically goes and has an offset to our own executable path. Okay, so again, we don't necessarily anytime will understand why does this thing or in that way or whatever. Just go with the flow. This is my tip for you, especially for the beginners. Go with the flow and learn. Of course, read as much as you can and go deeper into the waters as much time as you can. So basically, now it will take the argument list. So basically, it will define the argument for the C. So it will basically doesn't really, in this program, doesn't really takes argument from a user. For example, if you run this executable in CMD, it will not take an argument. For example, if you do this exe file space something, so basically it will execute itself. It's called argument 0, which is the argument itself, is the exe file itself. If you have argument 1, 2, 3, and so on, it's argument that you need to define. For example, if you run, for example, some type of a command.exe. So 0 is the exe itself, 1 is whatever argument that you need to define. 2 is another argument, 3 is another argument, and so on. Okay, so and then basically, then again, if we do F8, another value is pushed to the stack, as you can see here, into the top of the stack, and another push of this 3B2144, another, which is again another thing that is now pushed to the stack. And we have moved 3 to ESI. So now ESI is defined to be whatever something is the path. Now if we do F8 on move 3 to ESI, we'll see that it actually replaced the value that it had with the 3. So now we see the value of 3. Now it will go and do printf. Now if we do F7, it will literally, let me just close this window, it will go literally and go into this function itself. If we do F8, we can see push EBP, move EBP speed, the stack initialization process, which I explained beforehand, is the prologue. And it will do its magic. So for now, we don't see any prints here. Now if we do F8 on the VF printf, we can see the actual print, which is nice. Now we'll do its magic, clean up the stack, pop the last value to ESI. The last value, which was here, the 3, is popped to ESI. Now we have the pop of this address to EBP. Now we see the same address in the EBP, and return. Return will basically return us to our place. Now, if you remember, I said that the return value will be stored in the EAX. So now we have basically, and again, it really depends on the function that you have. Some functions have return values from one type, and it really depends on the developer that define the return values for the functions. And there are other functions that they don't have any return value because they are basically defined with this void without int or other type of return value. Okay, so we continue here, and again, it will go and do the same stuff. If we do again F7, we'll go into the function. Now it will do a printf, and sometimes IDA has problems with specific functions like printf, so it gets stuck. So we can stop it, run it again, try to execute it. Let's try it again, and now it works. So now we have the print for loop 0, and now it's fine. So now the EDI is 0. It will increment the INC instruction, increments it by 1. And now we have this add 8 ESP for the cleanup, compare 5 to EDI. So now EDI is 1. So it actually, the comparison will not be true. Okay, so it still, the EDI doesn't have the value of 5, so it does not compute. So basically, then the next instruction is basically jump lower. So if the value of EDI or of the comparison is lower than the value of 5, do again the same loop. Jump to this location 3B1060, which is again the address that, or the offset on the memory of the file. Again, to do this and that and this and that until it actually finished. Now again, I don't know why it has this bug with the printf. I don't really care. Just continuing. Now it seems to be fine for whatever reasons, and it will go for the same for the while loop. Print the calculations on operations. I will let you to do this for your own, and that's it for the video. If you have any questions, of course, just let me know. So thank you very much. See you in the next video.